All right, today we're going to talk about how our atomic models have changed since Rutherford's model. Rutherford's model, we had only the nucleus and the electrons discovered. Since then, when we come up to the time of the Bohr atom, we now know that there's protons and neutrons in our nucleus, as well as the electrons that are orbiting around. So Bohr's model is called the planetary model, and that's because he discovered and he went and proved that electrons were only in certain regions, and he called them orbits. The closer the electron is to the nucleus, the more stable the electron. So our center core electrons are the most stable. Those orbits, the ones that are closest to the nucleus, have very low energy. The orbits that are further away, or the further they are away, have higher energy. So if we have 7 orbits, the 7th orbit has the highest amount of energy. The first orbit has the lowest amount of energy, and they increase from 1 to 7. One of the things that Bohr studied was how electrons move and how they move between the orbits. So when you have an electron that is in a high energy orbit and it moves to a lower energy, that difference in energy, when it moves, gets emitted, and it gets emitted as light. So we see light being produced. So Bohr theorized that when these electrons move between orbits, they're either releasing energy when they drop down, or they're absorbing energy when they go from a low to a higher energy in a specific amount of energy. And his theory talked about these orbits. Those orbits were at specific energies besides the electrons themselves. This is great. This led into a lot of new things that we were unsure about, and we really hadn't talked about the electron much. But Bohr's calculations really only worked for the hydrogen atom. His calculations on these energies. So it was great, except hydrogen was the only atom that he could prove. But he started on some good thinking. So how do those electrons act? There is something that he discovered that eventually leads us to our most current model. But we're going to take a little side trip to talk about our electrons for a little bit. The electrons, the smallest particle, they take up the most amount of space, so they're very elusive. What we know about electrons is that they emit light when they move between orbits. So what is light? Light is produced when you have electrons moving from higher orbits to lower orbits. And we see this a lot of times as a visible light. So your spectrum, your color spectrum, Roy G. Biv. Visible light is a form of electromagnetic radiation, or EMR. So here is our electromagnetic spectrum. These radiations act as a wave. So waves move up and down. They have peaks and valleys. So what we're looking at is a bunch of different types of electromagnetic radiation. You will need to know this order. You need to know that radio waves have the longest wavelength, starting with AM, then shortwave, then FM. Microwaves are smaller than FM waves. And somewhere in here are your cell phones. I don't know the exact wavelength, but cell phones fall between your FM and your microwaves. Then you get into infrared, and we abbreviate infrared IR. Then comes this little tiny section that is your visible light. This is what we can see. I always remember that infrared starts with your red color. That's where the red spectrum is. So red, orange, yellow. Let's move yellow over a little bit. There we go. Green, blue, indigo, violet. So violet is our smallest wavelength. That's as small as we can go. After we are outside the visible range, we have our UV. Again, violet, ultraviolet. Violet is the smallest in our visible spectrum. Ultraviolet radiation we know comes from the sun. We have UVA, UVB, and UVC radiation, and they all are different wavelengths. Then we have our X-rays and Last but not least, gamma rays, which we learned about in radioactive decay. So know that order. There's a relationship between energy and these wavelengths, and that's some of what Bohr studied. He looked at how these wavelengths and the colors that he saw changed when there were different energies, and that's how he started to measure and quantize or take a mathematical approach to these energies. So low energies have long wavelengths, high energies have very short wavelengths. And we've come up with this equation. And the equation is C equals, we have a Greek letter lambda, it looks like an upside down Y, nu. Okay, so lambda, just spell it out, and nu, N-U. Lambda is our wavelength. And our wavelength is measured in meters. Our nu is our frequency. And frequency talks about how often it comes. We measure frequency in 1 over seconds, 1 per second. And C, we might have seen before in E equals mc squared. This is our speed of light. Speed of light is a constant. It does not change. It is 3.0 times 10 to the 8th meters per second. So on a test, I would give you this equation. Once again, you'd have to know what each of these mean. When we come back to school on Monday, we're going to be using this equation and the one that follows to do some calculations, and we're going to be calculating wavelengths and energies. So for now, know that C equals lambda nu, C being our speed of light, lambda being our wavelength measured in meters, and nu being our frequency measured in per seconds. So we travel on a little bit further, and we have this gentleman by the name of Max Planck. And he looked at the light emissions. So he looked at Bohr's work and tried to have Bohr's work fit with other elements other than hydrogen. What he discovered is light is not a continuous wave. What it happens is that it actually emits a small amount of energy, or quanta. They're little packets of energy. So he recognized that there's some relationship between our wavelength and our energy, and he was able to calculate it. So we have a tie-in to our previous equation. His equation that he worked on says E equals H nu. E standing for energy, and our energy is measured in joules, which is the capital J, J-O-U-L-E-S. H being his constant, Planck's constant. I'll write that for you in a second. Constant. And once again, we have our frequency term. So frequency is going to be our connecting point between our C equals lambda nu for wavelength and frequency, and our equation that we use, Planck's constant, E equals H nu. So he said H was equal to 6.626 times 10 to the negative 34. This is like a correcting constant. He wasn't able to get the numbers completely to agree, so he had to put in a number in between so that every time it works out. So we're going to pick it up from here. We're going to work on some questions when we come to school on Monday. And from there, we're going to learn about our most recent model, the quantum mechanical model. Have a great weekend, guys.